more detail, and to do this in part we're going to have to talk about something called combinations and Pascal's triangle. So the number of times that a particular term happens is related to how many ways you can count up the ways of a particular power can come about. It's easier if you look at the example. So if I'm looking at 2x plus 3 quantity to the fifth, it's the same as 2x plus 3 times, you get the idea, 2x plus 3 multiplied by itself 5 times. So in order to get an x to the fifth term, which you're going to get, that's going to be your highest power, I think you'd agree, that means you need to pick this 2x, this 2x, this 2x, this 2x, and this 2x out of each of these pairs of things and multiply them together. And that's the only way you're going to get it, which means you're only going to get one x to the fifth term. Great, you say. How does that help? Well, just bear with me. Now, what about the x to the fourth term? I think you'd agree there's an x to the fourth term, and that would mean what? Well, that would mean I'd have to pick 1, 2, let's say this one and this one to multiply, and that way I'd have 4 2x's being multiplied together to get to the x to the fourth. But that means, because I have to multiply everything together, that means I'd have to pick, like, say, this 3. So what have I done? In reality, what I've done is I picked 4 things, in this case 2x's, to multiply to get to the x to the fourth term. Okay? So one way that that could have happened is pick this 2x, this 2x, this 3, this 2x, and this 2x. Now I think you agree that if I picked this 2x, this 3, this 2x, this 2x, and this 2x, I get another x to the fourth term. And if you go through this logically, there are what? Well, I'd have to pick 4 2x's and pick only one 3, which I think you'd agree there are actually 5 ways of multiplying the 2x's together and picking one of the other 3's to actually get to the x to the fourth term. Now I'm not going to belabor this, but by the time we get to the x to the 0th term, right, how many ways are there of picking that? In other words, getting an x to the 0th term. Well, to get the x to the 0th term, what we'd have to make sure to do is what? Not pick any x's to multiply. How many ways are there to do that? Well, I'd have to pick all 3's, right? Which means that there'd only be one way to get the x to the 0th term. Now it turns out this is a combination, as in what we're doing is we're picking a subset, in this case of 2x's, out of a bigger set. That is, there's 5 of them to pick from, if you will. And we don't care what order we pick them in, but we're just counting up the number of ways that can happen. That, as it turns out, is a combination. So this does lead to combinations. The number of it's picking a set of objects from another without picking the same object more than once and without worrying about the order in which they are picked. For example, now you guys can read, but I'll read it to you anyway. If I pick, now this is set notation, so this is telling me I got the letters A, B, and C. How many ways are there of picking 2 items from this set? I think you'd agree. I could pick A and then B and then A and then C. And I'm kind of making an ordered list here. And then B, I could pick B and then A, and then B and then C. And then I could pick C and then A and then C and B. Now I think you'd agree, however, that some of these, if I don't care about the order in which they are picked, that some of these, like this AB and this BA, aren't they really the same? Right? So what happens is, it turns out I'm overcounting if I just list off all these possibilities, because take a look, there's AC, there's CA, those are the same too. As a matter of fact, because here's BC, and he gets a different color, here's BC and CB, same thing's happening. So in reality, what has happened here is I've got 2 letters that I'm picking, 2 letters, 2 spots that I'm picking, right? I have 3 letters to pick from for the first spot and 2 letters to pick from the second spot, which is 3 times 2, or 6 different possibilities. But then I'm dividing that by, well, how many different ways are there of ordering up those 2 things? 2 times 1, or 2, which means 6 divided by 2, or 3 distinct ways of picking these 2 letters. So AB would be an answer, but BA is the same, so we wouldn't count it. Same with CB and same with CA. So these would be the 3 final things. Okay? So it turns out when we're talking about a combination, I'm just going to show you some notation here. we sometimes say N, C, K, where N is the number of things picked from, number of things we're picking from, and then K is the number being picked. So this could be written as NCK, guess C stands for combination, or it's kind of this N over K. An example would be 5 choose 3 would mean from 5 objects, pick groups type of 3. So what does that mean? Well, there is a formula for all this, but I'd like to show you something called Pascal's triangle, which then relates to these combinations. So Pascal's triangle, so this is a way of doing this. Think of it this way. This is a series of entries. In this first row, there's 1 entry. In the second row, there's 2 entries, and so on. Now, typically what we do is, and we can do this a couple of different ways, but typically what we do is we say that this first entry is actually the 0th entry, 0th, right? So we start counting at 0. So that means this would be the 0th, this would be the first, 0th, first, and second, and so on. Now, if you're looking at this, you probably see some sort of pattern, I hope. At the very least, it's a triangle, right? Also, that all seems to start with 1. So here's how this works. It turns out that this is, if we think about it this way, this 0, this would be, well, equivalent to, this row would be equivalent to 1, choose 1. In other words, how many different ways are there to pick one thing from a group of 1? The answer is 1. And then this would be 1, choose 0. That is, how many ways are there to pick 0 things from one object? Well, there's only one way to pick nothing, thus the answer is 1. Now it gets interesting once we get down to the remaining rows, which means that this row here is equivalent to 2 choose 2, 2 choose 1, and 2 choose 0. Now how does this relate? Now if you remember way back when we did the expansion of x plus 1 squared, it ended up being x squared plus 2x plus 1. And when we did the expansion of x plus 1 cubed, it ended up being x cubed plus 3x squared plus 3x plus 1. So hopefully you see, especially if I throw a 1 in front of here and here, that this corresponds to this row and this corresponds to this row. Now, it turns out that these numbers match exactly in this case because the coefficient of x is 1 and this is just a 1. Your answer is going to get slightly different for the coefficients if you change what the numbers are, but we'll talk about that in subsequent videos. Now, Pascal's triangle is pretty easy to set up, and I just want to talk quickly about a couple of patterns here. How do I know it's 1, 2, 1? Well, take a look. What is 1 plus 1? How do I know this is 1, 3, 3, 1? 1 plus 2? 1 plus 2. Now, if you look carefully, 1 entry, 2 entries, 3 entries, 4 entries, 5 entries, and so on. The 1, 2, these numbers, these second numbers, correspond to what? The power. So n, that is the power that you're doing, would be these different things. So if you were looking at, say, x plus 1 to the 6th, you'd be looking at this row right here. And we know that we'd have 1 x to the 6th. Apparently we'd have 6 x to the 4th, and you get the idea. And how we can set this up, that is how we can actually come up with what these actually are, is because when you add 2 entries, 2 adjacent entries, 2 entries next to each other, that gives you the entry just below and between it. Okay? So we're going to put this into play here in the next video when we actually start expanding.